Uh, Welcome everyone to this special event. My name is Akshay Naik. I'm a faculty member here at ISC, and right now I'm filling in for Dean Kaushal Verma, who couldn't be here because of an urgent meeting. It's an absolute pleasure and honor to have Professor Serge Haroche with us for this public lecture. The lecture was enabled by Savita and French Consulate on the France side, and IQTI and Quantum Research Park on the IISc side. IQTI, if you don't know, is an initiative, IISc Quantum Technology Initiative, that has been running in IISc for the last 2.5 years. It includes faculty members, about 40 faculty members from about 12 to 15 departments in IISc, who work together on various aspects of quantum technology. So if you're interested in knowing about this, you can visit our website, and there are internship opportunities if you like. Okay. So we'll get started. We have with us Consul General of France in Bangalore, Mr. Thierry Berthelot. So I request him to say a few words before we get started.
So, ladies and gentlemen, distinguished guests, it's really a great pleasure and honor for me and for my colleagues to be here tonight in this prestigious Indian Institute of Science to attend the talk Professor Serge Haroche will give about the history of the science of light, a reflection about the connection between basic and applied science. I reminded yesterday how important it is to talk about science to a large audience like here today, and I'm glad to see so many of you, as it is necessary to explain what are the current and coming challenges and how science can help us to understand them better. Dr. Serge Haroche became Nobel Laureate in Physics in 2012, jointly with Dr. David Wineland, for their work on groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. A study of the particle of light, the photon. Ladies and gentlemen, France is well known for, guess what? Food, for wine, for literature, maybe now for football, for strikes and demonstrations, but I'm not so sure that many among you are aware that 73 French people have been Nobel laureates since 1901. 73. Names like Georges Charpak, Gérard Mourou, or Alain Aspect may ring a bell to you. They received the Nobel Prize in Physics too. Or maybe at least are the names Marie Curie, Emmanuel Charpentier, who was, by the way, a recent keynote speaker at the Bangalore Tech Summit, or Esther Duflo, familiar to you. All of them are French women who've been Nobel laureates in physics, in chemistry, and in economy. As you know, there is no Nobel Prize in mathematics. It is in this domain the research work excellency is rewarded as a field medal. 13 French mathematicians have received the prize since 1936. Last one was Hugo Duménil-Copin last year, 2022. I won't go through a long list of all these laureates France is proud to have. But I'd like to share with you some figures that will give you an idea of how France is ranked. First, France is the fourth nation in the world in terms of number of Nobel laureates, the fourth. Second, France is ranked number 2, just behind the US, for medal fields, so in mathematics, number 2 in the world. It is therefore a fantastic opportunity to welcome Professor Serge Haroche in Bangalore, and I would like to thank him and his wife Claudine again for being with us today. Ladies and gentlemen, some of you may wonder how a rather small country in size like France has been able to reach such research successes. Well, let me share with you a couple of ideas that can explain these achievements. First, by the public funding and private funding of the research. Every year, my country, France, dedicates 2.25% of its GDP to public research. It is not the best ratio we can observe in the world, but it is above the European Union average, which is of 2%. In addition, I would like to say that the French Ministry of Finance proposes a very attractive measure. We call it Crédit Impôt Recherche, which could be translated as income tax payback for research investment. Companies investing in R&D received an income tax discount. Such measure encourages private investments in R&D, and companies are then keener to work with academic institutions under the private-public partnership agreement. Second is what we could call internalization of the French system. Dear friends, today 42% of the PhD students in France are not French. They are coming from all over the world. And this diversity is fruitfully enhancing the research activity in the French labs. You don't need to speak French to go to study in France. This could be a surprise to you, but I repeat, today you don't need to speak French to go to study in France. To do your PhD or your postdoc in France. But knowing French language, of course, will add value to your stay and help you finding a job later. I could also have mentioned French innovation ecosystem, which contributes to a disruptive approach of science. But I'll stop here, and I hope my points have raised some interest for those of you who were not familiar with France's higher education and research system. So I'm looking forward to have more candidates in the future for PhDs in France among you. And of course, our office in Bangalore, the Consulate General of France, is here to help you with Campus France office also to find the best plans for your studies in France. I thank you for your attention, and I wish you a very good evening. Thank you.
Can I request Professor Nitin Said to say a few words about Savita and how it's promoting the research here?
Thank you, Professor Akshay. I'll not be taking too much time and standing in between light and you. So I'll be very brief on that. For all others who are not aware that what Savita is actually an Indo-French Center for Promotion of Advanced Research. We provide funding supports for research. So all my friends, scientists, researchers, students also, we have a mobility support programs. We have a scientific research collaborative programs. I'm not taking time to explain on this because today we are not here for all these programs. Do refer to Savita website. In case of any difficulty, you can write to us. So first and foremost, I would like to thank Professor Serge for agreeing to the invitation, which is as per the mandate of my co-chairs, that is Department of Science and Technology Secretary, and the Ministry of Europe and Foreign Affairs in France. Savita is mandated by these two, so they instructed us to go for the best of the knowledge exchange programs, creation of a knowledge exchange programs. And thanks to the Council General also, who recently pointed out that French side has got 73 Nobel laureates. So we're trying to have maximum from India also going to France and French also coming to India. Last month we had Professor Jean for economic sciences. So thanks embassy side on that, and thank you Excellencies for facilitating the contact with the Nobel laureates and requesting on behalf of Savita for these facilitations. And thank you Professor Serge for agreeing to it. Thanks Mrs. Claudine also. So I'll be very short on that particular point, that Savita is a platform, knowledge generation platform. We always support any researcher, any scientists on this. So I'll close my talk at this point of time, and thank you very much for IISc hosting such a beautiful lecture. Thank you, Professor Arindam and Akshay. Thank you. Thank you.
Okay, so I'll just briefly introduce Professor Haroche. Professor Haroche received his doctorate from Paris via University in 1971. Then he did his postdoctoral work at Stanford. After that, he was a professor at Paris Via University and Ines Paris till 2001. Since 2001, he's been at Collège de France, first as a professor, then the president, and since 2015, he's working there as Professor Emeritus. Okay, he has many awards to his name, including Quantum Electronics Prize of European Physical Society, Charles Townes Medal, CNRS Gold Medal, Herbert Walton Award. In 2012, he received the Nobel Prize along with David Wineland for his pioneering work in quantum measurements. He did some groundbreaking work that enabled quantum measurements and manipulation of individual quantum systems. Today, he'll be giving a general lecture on the connection between basic and applied sciences. Professor Haroche.
Okay. Okay, so it's a great pleasure to be here, and I would like to thank the Consulate General of France here in Bangalore, the Savita, and the IISc for organizing my visit and for inviting me to give a talk here today. I must say I'm impressed by the large audience on a Saturday afternoon. I'm not sure that in France I would get so many people, but it's very pleasant. And I am glad to talk to you about the science of light. And this will be an opportunity for me to discuss the connection between basic and applied science, which I think is a very important topic today. There is a lot of money which is put in science today, and it's important that a large fraction of this money go to basic science, as I will explain later on in this talk. There are several reasons for me to have chosen this topic. First of all, of course, it's because light and the study of the light, interaction of light with matter, has been my passion during my career, which has started at the time when the laser was invented. And I was very lucky to have started my research at a time when this source of light, which is extraordinary, which has fantastic properties, was invented. And I have followed not only in my own research, but in the research of all my colleagues throughout the world, the fantastic discoveries and inventions which have been made in basic and applied science with lasers. The second reason is that I think that studying the history of the acquisition of knowledge about light since the 17th century, which is the beginning of the scientific method, is interesting because it shows how the scientific method has emerged and the progress it has known from that time on. The mixture of observation, experiment, and theories helping each other and allowing us to make a lot of progress in fundamental knowledge and also in applications. Now, these two perspectives are, of course, linked. When you are a scientist, you have the deep feeling that all what you are doing is continuing an adventure which has been started before you, and it has been said that today's scientists are, in fact, sitting on the shoulders of the giants which have preceded them, and we will see a list of these really outstanding scientists which have been involved in the science of light. What I want also to discuss is that there is a continuous path going from the beginning of this history in the 17th century with the work of Galileo, for instance, and what we see today. For example, the quantum science that we see today has not come for just appear suddenly. It is a continuous story which has been built on generation of scientists, and I would like to give this feeling in this talk. Now, I have been lucky in my career. I have been lucky because when I was 20 years old, I joined an exceptional lab, the Kastler-Brossel laboratory at École Normale Supérieure in Paris. This picture was taken on the day of Kastler Nobel Prize announcement in October 1966. Alfred Kastler, who is at the center of this photograph, was awarded the Nobel Prize for the discovery of optical pumping, which is the first method using light to manipulate atoms, the internal degrees of freedom of atoms, but then on a lot of experiments have been doing which extended Kastler's study to study, for instance, how light can be used to slow down atoms, to trap atoms, and this is the Nobel Prize of Claude Cohen-Tanucci in 1997. Jean Brossel, which is on the right part of this picture, was the head of the lab at that time, and you see I am in the back here. I'm not sure you can recognize me, but since you are doing statistics, on this picture you see 20% of the physics Nobel Prizes, 3 out of 15 altogether. So this just shows that this lab is a fantastic place, and I was very lucky when I arrived there, quite by chance, to start my career in this atmosphere. The second luck I had, of course, I already mentioned it, is to have started just after the laser was invented. At that time, we had no idea of what the laser would be useful for. We just had an intuition that this source of light, with its remarkable properties, would be used to do things, but we could not imagine all what has been done since then. And this is so, what I want to stress to start with is that a scientific career requires a mixture, a combination of passion, of curiosity, of course, of intuition, and of luck. You have to be lucky to be at the right place at the right time, and this is what I have found in my own career. I want also to mention the excitement to participate to a collective adventure. We when you do research, you are not just working in your lab, you are working with many, many colleagues throughout the world, and you collaborate with them. These colleagues have different cultures, different backgrounds, but they all share the same passion for science, the same curiosity, and you are part of that adventure, which is a spatial adventure, but it is also a temporal adventure because, as I said before, you are part of a flow of discoveries which goes through the centuries, and you have to feel that very deeply, and this is a big advantage, this is a big privilege we have as scientists. Now, talking about light, I don't think it's very useful to remind ourselves that light is the carrier of most of the information we receive from the world outside us and from the universe. And this is one reason, of course, to be interested in light. Clearly, from the prehistoric times, mankind has worshipped light because it's so important, because it gives us information, also because it gives us the energy that is essential for life. And so mankind has worshipped light through myths and religions. And you see, for instance, on the right part of this slide, a painting coming from ancient Egypt showing the rays of light going from into the eyes of a princess on the right. And there seems to be here a premonition of the photon. There's a feeling that light is made of particles, but of course this was just a coincidence. And the science of light did not start at that time. You have, of course, the first scientific knowledge about light phenomena came from the antiquity and from the Muslim Middle Ages. But it is only in the 17th century that truly quantitative theories about light were developed. And when I say quantitative theories, I mean theory based on measurements and relating light to phenomena which can be described by mathematics. And this is what I think is a scientific method about. This history has, of course, been illustrated by a very large number of bright minds, not only scientists and physicists, but also philosophers. And I just show you here a gallery of these people starting in the 17th century, from Galileo, Descartes, Fermat, Huygens, and Newton. Then in the 19th century, Young, Fresnel, Ørsted, Ampère, Faraday, and Maxwell. And in the 20th century, from Planck, Einstein, Bohr, De Broglie, Heisenberg, Schrödinger, Dirac, and Feynman, and so on. And I could have listed more of these people. But all these people, in one way or the other, have had very important contribution to the story I'm going to tell you today. What does this story teach us about science? And I would like to make a few points. The first point is that, of course, the history of light has accompanied, as I have already said, the birth of the modern scientific method, which is based on observation. Then you try to reproduce this observation by doing controlled experiments. And from observation and experiments, you try to build mathematical theories which put a global context to all what you have been observed. This theory predicts new phenomena. If these phenomena are observed, the theory is vindicated. If these phenomena are not observed, or if other phenomena are observed, you have to give up the theory and go in another direction. So science is made of doubt, but rational doubt, and constant back and forth between experiments and theories. And there is no place there for fake news. Observations are real. And for opinions. Theories are not opinions. Theories are based on the observations. The second point I would like to make is that there is, of course, a symbiosis between curiosity-inspired basic science and technology. And one cannot go without the other. For example, the first discoveries about light that I will be discussing today have been made possible by the invention of instruments to measure space and time. The Galilean telescope for measuring space, and the pendulum clock to measure time. And before that, only speculations about light could be made and no scientific knowledge. Once these first discoveries about light have been made, conversely, the knowledge which has been acquired has led to the development of more precise devices. For example, reflective telescopes, the Newtonian telescope, prisms and gratings which spread out the spectrum of white light into a rainbow of colors. This is the beginning of spectroscopy. Interferometers, which make spectroscopy more precise. And finally, in the 20th century, lasers and devices which exploit visible and invisible light, microwave and X-rays, which are light that you cannot see, but which have exactly the same properties as visible light. And the invention of this instrument has made possible more precise observations at the end of the 19th century, observations which have led to the theories of relativity and quantum physics, which have completely modified our vision of nature and given birth to most of the modern technologies that we are using in our everyday life, with the hope that new technologies will emerge in the future, and this is the topic of the quantum technologies we are talking about today. So there's a continuous flow of discoveries and inventions coming from the 17th century. All started with two instruments at the origin of modern physics, the Galilean telescope and Huygens' pendulum clock. And in fact, the pendulum clock comes from observation of Galileo, who observed that the period of a pendulum is independent of the mass of the pendulum, depends on the length in the gravitational field of the Earth. So in fact, you can say that Galileo was at the origin of these two instruments. And Galileo was also the first person who tried to measure the velocity of light. Before Galileo, one thought that the light was instantaneous, that it was just filling space instantly. And Galileo had the feeling, the intuition that it was like sound, that it took some finite time for light to propagate from one point to the other. So he tried a very simple experiment. He had a lantern standing on a Toscan hill. One of his assistants was standing on a nearby hill a few kilometers away. He uncovered his light, and he asked his assistant to do the same when he received the signal. And he tried to see what was the time it took for the light to go back and forth. And of course, the result of the experiment was negative. He did not see any delay. This is because light is going too fast for that. It took only a few microseconds, and our brain is unable to distinguish these short times. But what is interesting is that Galileo forgot about that and didn't think about that anymore, but the instrument that he used for the first time, the telescope, the refractive telescope, was instrumental to do the first measurement of the velocity of light. You see here on the right side, Jupiter and the four satellites of Jupiter. This is a picture, I think maybe Galileo saw that in this way. This is a picture you can take today. We just take just a standard camera, you put it on a tripod, you look at Jupiter on a clear night, and you see these four small spots around Jupiter, which are satellites going around. This was very important because it was the first example of a planetary system outside ours, and it was vindicating Copernicus' view that the planets were going around stars and satellites around planets. But what is interesting here is that this was a clock. The time it took for Io, which is the satellite closest to the planet to go around, was a kind of natural clock which could be seen everywhere in the world and which could be used to make measurements of time helpful for navigation, for instance, to be able to compare the time at a given point with the time at, for example, in Paris. And so an astronomer in Paris, in fact a Danish astronomer, was asked to record the time at which Io was coming out of the shadow of Jupiter. So this was already an example of international collaborations. Romeo was a Danish astronomer working in Paris, and this is an example of the science in France, because the place where the velocity of light was measured for the first time was Paris. So what did Romeo do? He just recorded the time at which successively the satellite was going out of the shadow. And he needed to use a Huygens clock for that. So he made this measurement. And what he realized immediately is that the apparent period he saw was increasing during 6 months. So it took, Io was coming out later and later each day by a few seconds per day. And so the clock had to be rather precise. And during the next 6 months, it came earlier, a few seconds earlier each day. And he realized that this was due to the fact that the Earth was receding or going back towards Jupiter. And the time it took for the light to travel along the path that the Earth had gone during the time Io was making one turn was important. And so he made this kind of drawing in the published proceedings, and he found a delay, an accumulated delay of 17 minutes during 6 months, which he said was the time it took for the light to go across the diameter of the Earth's orbit around the Sun. And at that time, astronomers had measured the size of the Earth's orbit. 17 minutes is twice 8.5 minutes, which is the time it takes for light to go from the Sun to the Earth. So Romeo measured that and did use the velocity of light, not with a high precision, but it was the first measurement. What I insist upon here is that the clock was, of course, essential. And the clock that Huygens used was a mechanical clock. The period was 0.5 seconds. And the uncertainty was about 10 minus 4. That is 1 part in 10,000, few seconds per day. Today, atomic clocks, and I just don't want to enter into details, which are based on the oscillation of electrons in cesium atoms, oscillate at 10 billion times faster, in fact, 10 orders of magnitude faster, and their precision is 10 billion times higher. Not 10 seconds per day, but 10 minus 1 nanosecond per day, which gives an uncertainty of 1 part in 10 to the 14. And these clocks are carried by satellites, and this is the basis of the GPS system. So you see the continuity between the idea of Galileo to use the motion of Io around Jupiter to do navigation and what we achieve today. And this improvement of 10 orders of magnitude measures the progress that science has made in 2 centuries. And this, in fact, these atomic clocks are the atomic clocks of the 1980s. We are 40 years later now, and in the end of the talk, I will show you that there is a 5 order of magnitude increase in the precision of optical clocks today. So what we could do with the clocks today is certainly fantastic, but we don't know exactly what it will be useful for, because now the GPS has a precision of about a few meters, and with 5 orders of magnitude better, we have a precision of a few micrometers, but I don't think it's useful to be able to localize ourselves to the surface of the Earth within a few micrometers. But there may be other applications, as we will see. So at that time, 17th century, there were 2 conflicting theories about light. Huygens, who is a Dutch physicist working in France, again, international cooperation. He was working at the French Observatory in Paris, had the idea that light was a wave. It was a kind of wave propagating through space, like acoustic wave. And the wavelength, the distance which separates the crest of the wave, was different in air and in water. The waves were a little bit more closer to each other in water, according to his model. And this explains why when light is refracting from air to water, the light comes closer to the normal, to the surface. That is, the incidence angle is larger than the reflective angle. This was known since Descartes and Snell. It was called the sign law, Snell's law. It was an empirical law. One did not know why it was so. And Huygens had the idea that it was due to the wave nature of light. At the same time, Newton in England had the opposite view. He said that light was made of particles, and since light is going closer to the normal, when it goes into water, it means that there is a kind of force which sucks the particles inside the water, which accelerates the particles. So according to his theory, light was going faster in water than in air. But since nobody had measured the velocity of light in water, the 2 theories were still open to investigations. Both theories are based on Snell's law, but with quite different interpretation. According to Huygens, the sign of the incidence over the sign of the refractive index is the velocity of air over the velocity of water, and according to Newton, it was the opposite. So the question was open, but since Newton was very famous for his law of mechanics, and especially the law of gravitation, he was, people were standing more on the side of Newton than the side of Huygens during the whole 18th century. But I stress this because I think Huygens is underestimated. Huygens is really a fantastic physicist. He was also an engineer. He was able to transform Galileo's idea, which was just a theoretical idea, into a very precise pendulum. And he made very important advances in mechanics. He's the first one who discovered the centrifugal force, for instance, and in optics. At the beginning of the 19th century, the experiment of Thomas Young and Fresnel vindicated the wave point of view. They observed that if you separate, for instance, a light beam into two parts and let them recombine, you see three interferences. You see that at some point in space, the two wavelets contradict each other. One is going up, the other down, and so you have a place where you don't have light. So you see that sometimes light plus light gives darkness. And this is only possible if you interpret light as a wave. At the surface of a pond, if you have two sources of vibration, they combine and give rise to this kind of interference effects. Fresnel did the same kind of experiment in Paris, and he did a very dramatic experiment in which you look at the shadow of a disk, and in the center of the shadow you see a bright spot. And this is completely impossible to understand with a particle theory. With a wave theory, this is just due to the fact that all the points at on the circle radiate in phase at the center for symmetrical reasons, and you must have a bright spot. In fact, there was a mathematician at that time, Poisson, who was a mathematician in the French Academy of Sciences, who pointed that it's completely stupid to imagine that you will have a bright spot in the center, and so that the wave theory should be wrong. And then the experiment was done in front of the Academy, and the bright spot was discovered. So it's called the Poisson-Fresnel spot, and people say that this was the dramatic experiment which vindicated the wave theory. This is more a story, a legend than a real story, but it tells something about the kind of discussion that scientists had at the beginning of the 19th century. It took a lot of time for many scientists to accept that light was a wave. And the question was, of course, at that point, what are these waves made of? What is vibrating? What is oscillating? In which medium do these waves propagate? And this started the questions about the nature of this hypothetical medium which propagate light waves called the ether. And the whole 19th century was full of theories about the ether. The point which was important was to measure the velocity of light in matter. This experiment was crucial because it was really the problem over which Huygens and Newton had been fighting. So the experiment could be done, in fact, in the middle of the 19th century, measuring light velocity. It was the physicists took again Galileo's idea, but using 19th century technology. So the first physicist who did that was again a French physicist, Fizeau, who used a kind of a wheel with tooth at the edge of the wheel, rotating very fast, and this tooth was chopping a light beam, transforming the continuous light beam into a succession of short light pulses. These pulses were propagating over 8 kilometers from the suburb of Paris to Paris, and then back. There was a mirror. It was not an assistant of Fizeau. It was just a mirror reflecting the light back on its track. When the light came back on the wheel had rotated a little bit, and the dent in the wheel was replaced by a blocking piece, and so the light was stopped. And knowing the distance that the light had traveled and the speed at which the wheel was rotating, he measured the velocity of light, which is close to the one we know today. But of course, since the experiment was made over 8 kilometer distance, there was no way to fill this distance with water. So the experiment had to be done inside a lab. And the first person who did the measurement of the velocity of light in a lab was a colleague of Fizeau, Foucaults. He replaced the rotating wheel by a rotating mirror using the setup that I show you here. A light beam is going from right to left, impinging on the mirror, which is rotating very fast. And this mirror sends the light on two concave mirrors here and there. On one of the paths, you have a long tube filled with water. Then the light comes back. When the light comes back, the mirror has rotated a little bit, And so the beam coming back is deflected by a small angle, and you measure this small angle with an eyepiece here, which for which the light is reflected by a semi-reflecting plate, and you see spots which are slightly displaced from the upper and the lower beam. And by just looking at the relative displacement, you can make the ratio of the velocity of light in air with respect to the velocity of light in water. And Fizeau discovered that the velocity in water is indeed smaller than in air. It takes a longer time for the light beam to go from one point to the mirror, the bottom mirrors and the upper mirror. And this was the end of, one saw the end of the wave theory of light, of the particle theory of light. It vindicated the fact that light was a wave. But a wave of what? To discover that, we had to wait for the convergence of another line of experiments that I don't have time to discuss too much, which was a burst of electrodynamics. People had recognized since the end of the 18th century that currents were producing forces on magnets, and that moving a magnet in the vicinity of a circuit, you induce a current in the circuit. And this connection were made by scientists like Ørsted in Denmark, Ampère in Paris, and Faraday in England. They did a lot of experiments measuring the reciprocal effects of electric currents on magnets, and Faraday introduced the notion of electric and magnetic field lines, the fact that space is full of lines of electric and magnetic field which describe how an electric particle or a magnetic moment would be kind of forces it would experience from this field. So this field notion was very important, and it made Maxwell in England reflect about this, and Maxwell combined Ampere's and Faraday discoveries into a theory of electromagnetic waves. What he discovered is that the variation of an electric field in space produces a magnetic field, with variation produce an electric field, and so on. And these two fields feed each other and propagate through space. And he wrote this equation, and this was really, as I say right here, a great piece of research, because it unified electricity, magnetism, and as we see, optics. What you see here, this page is displayed at the Royal Society in London. It is a page on which Maxwell comes to its conclusion. I have at the top of the page, I don't think you can really read it here, but he has been able to calculate the velocity of electromagnetic waves. And what he found is that this velocity was given, related very simply to epsilon and mu, which are the constant of electrostatics and magnetostatics, constants which were introduced by Coulomb and Ampère to describe the forces of particles between each other and the forces of magnets and currents. And these constants were known. Putting them into this formula, he found a velocity which is very close to the velocity that Foucault had just measured in Paris. And so he quotes these two values, and then he concludes, and these are the three last line on this page, the agreement of the results seems to show, so this is a British understatement, seems to show that light and magnetism are affection of the same substance, and that light is an electromagnetic perturbation propagated through the field according to electromagnetic laws. So he made a giant leap by saying that, in fact, electricity and magnetism and optics were the same thing. It was the first great unification in physics based on equations, on Maxwell's equation. And of course, this has had tremendous consequences. What Maxwell has proven is that light, visible light, is just a small window in the spectrum of possible radiation, that at longer wavelengths, infrared, microwave and radio frequencies, you have radiations that you cannot see but which exist. And the same on short wavelengths, you have UV and then shorter radiation. And of course, they have been discovered. And so this is again a connection between basic science and application. Hertz in Germany was looking for these radio waves, and he discovered them. On the other side of the spectrum, Röntgen was not looking at them, just stumbled on them, observed something that he didn't understand, and later on it was discovered it was a short wavelength electromagnetic radiation. And of course, I don't have to insist on the importance for technology of these discoveries. All our cell phones today work on the reception of radio waves. The cosmic background radiation, which gave birth to cosmology and astrophysics, is detecting this long wavelength radiation. And on the short side of the spectrum, of course, X-rays have been absolutely essential in medical studies and also in the discovery of the structure of matter, condensed matter, crystals, and so on. So this has been very important, but even more important than that, by making more and more precise measurement on the spectrum of this radiation, puzzling questions have been raised, which have led to relativity and quantum physics. And so I would like now to elaborate a little bit on that. In the year 1900, just after Röntgen work and just after the electron had been discovered by Thomson, Lord Kelvin, who was the Pope of physics at the time, used to say that one knew almost everything which needed to be known about the physical laws, except for two small clouds which were still intriguing. And so he said at the beginning of a talk he gave at the Royal Institution, the beauty and clearness of the dynamical theory which asserts heat and light to be mode of motion. So the idea is that the heat is due to the motion of the atoms inside matter, and light is, the light produces heat, which is due to the motion of the electric and magnetic fields. So this mode of motion cannot explain two phenomena. One phenomenon was the ether puzzle, the fact that it was assumed that Maxwell's equation describe the velocity of light in the medium called the ether. And if you move through the ether, like the Earth is moving around the sun, then you should measure a velocity for the light in your own rest frame, which is different from what it is in the motionless ether. And no difference was observed. There was the famous interferometric Michelson experiment, which was unable to find any difference in the velocity of light when you measure it along the motion of the Earth or in a direction normal to the motion of the Earth. And so it was very puzzling for the ether. And in fact, the solution was given by Einstein, who said Maxwell's equation should be valid for all observers. And this was again an old Galileo's idea. Galileo said there is no way if you move in a boat to find out that you're moving unless you look outside. If you drop a ball, it will fall at your feet exactly if you were on the motionless. And it was a very important notion by Galileo that he expressed to try to explain to the people who thought that the Earth was at the center of the universe that the absolute motion has no meaning. And the only thing Einstein had to do is to extend that to all phenomena, including electromagnetic waves. He said Maxwell's equation should be valid for all observers, but if we do that, it means that the velocity of light should be the same for all observers. But if you state that, it means that the time and the distances cannot be the same for all observers, because if you use Newton's equation based on absolute time and absolute distances, you have the addition of velocities laws, which comes from there immediately. So he had the boldness to give up the absolute value of time in order to understand this puzzle. And it was the start of relativity, which tells us that the time does not evolve at the same rate depending upon your velocity. And this is essential for the GPS. If you don't correct for the fact that the clocks in the GPS are slower than the clocks on Earth, the GPS will be wrong. And then he extends that to general relativity. Again, Galileo's idea, the fact that all masses fall at the same speed, is induced Einstein to equate uniform motion to the existence of gravitational fields, and then it led him to understand that a clock does not tick at the same rate whether it is in a high gravitational field or in a low gravitational field. And this is again a correction that has to be made for the GPS clock. So this one, I don't have time to elaborate on that, but one of the clouds led to the relativity, which has very important consequences. The other cloud was even more important. What people had realized at the end of the 19th century is that the the light, the electromagnetic radiation produced by heated bodies could not be explained by classical physics. You know, if you look inside a furnace, you see light, you see red light, or you see white light if the temperature is higher. And the spectrum of light, which is radiated by heated bodies, is a very simple phenomenon everybody observes. And what is very strange is that if you use Maxwell's equation and the laws of classical thermodynamics, you find a result completely different. You find that the light should have more and more energy at shorter and shorter wavelengths. So it's absurd. It's what's called the UV catastrophe, the ultraviolet catastrophe. And this was the cloud that Lord Kelvin mentioned. And again, the solution was quantum physics, the fact that the exchange of energy between matter and light took place by discrete quanta, and that light itself was made of discrete quanta. And this was the beginning of the quantum age. And of course, the researcher who was at the start of these two revolutions was Albert Einstein. And in 1905, he wrote one paper about relativity, one paper about the photon, the fact that light is quantized, and two other papers, one about the Brownian motion, which demonstrated that atoms and molecules did exist, and one paper with the famous formula E equal mc squared, which shows that there is a huge amount of energy in each piece of material. So this was a fantastic year for physics and for Albert Einstein, whose career started from then on, as you all know. So in fact, at that time, quantum technologies were absolutely impossible to imagine. In the year 1900, there was a World Fair in Paris, and a lot of hope and a lot of optimism about the evolution of the world at that time. And people were asked to imagine what would be the technologies of the year 2000, 100 years later. And postcards were published, and you see the kind of things which were predicted. I like the one on the right, which shows that people were supposed to be heating themselves with a piece of radium in the fireplace. So you see, it was a very strange prediction of nuclear energy. And you see how the mails would be transported. So they could not imagine email. It was just a very extrapolation over the first flying machines of that time. So this was of course, very naive, and I use this kind of postcard as a warning for us who are supposed to imagine what the quantum technologies will produce in the years to come. I think we have to be very humble and very cautious not to make too much prediction extrapolating over present knowledge. Quantum technology were, of course, not anticipated. Nobody predicted just the classical computers that I'm using. Even if it does not work all the time, it's still good. Lasers, atomic clocks and the GPS that I already mentioned, MRI scanners, which are based on at least 3 quantum technologies. You have to understand nuclear magnetic resonance, which is a quantum effect. You have to have high magnetic field produced by superconducting coils, which is another quantum effect. And of course, you need computers to transform these signals into images, which is, again, due to explained by the behavior of transistors, which require also quantum knowledge. So these quantum technologies were not anticipated. So on which kind of ideas are based all these new technologies? I have tried to summarize this on this slide, and I call it the Pandora box of quantum physics, because the box that Einstein opened did not please him at all. He did not like what was coming out of this Pandora box, and I will say a few words about that. So the idea is that light is at the same time a wave and an ensemble of particles, and apparently Einstein reconciled Huygens and Newton. The wave aspect is important to describe the propagation of light, and the particle aspect is important to describe how light interacts with matter. When you have a detector, you get a click for each photon, so there is a discontinuous click which demonstrates the fact that light has a particle aspect. This dualism has been extended a few years later to matter. Electrons, atoms, and molecules behave at the same time as wave and as discrete entities. This is the idea of De Broglie. I must say that another important person who had a hint about that was Bose in India. Bose had a special statistics for describing photons, which he discussed with Einstein, and Einstein, from Bose's idea, had a hint that light was made of photons again. And when the Broglie paper was presented to Einstein, he was able to make the connection between Bose and the Broglie's idea, and it gave him the feeling that these two young people were unveiling part of the big mystery of quantum physics. And it took only 2 or 3 years from then on for the work of Heisenberg and Schrödinger to develop the mathematical framework of quantum theory. So what we know now, and what was discovered around that time, is that the wave associated to a particle is an amplitude whose square is the probability to observe the particle in each point, provided a measurement is made. And this means that the theory is non-deterministic. The only thing you can predict is the probability to find the particle here or there. And if you redo the same experiment over and over with the same initial conditions, you will find different results according to these statistics. And this was completely opposite to the classical idea that if you give us a position of all the particles in the world, you can calculate and find out what the future is about. And Einstein didn't like this non-deterministic view about the universe. So another way to state it is to say that the position, the velocity, or the trajectory of a particle has no physical reality before you observe it. Before you observe it, the particle behaves as a wave, which gives rise to interference effects, as long as you don't attempt to localize it. If you try to find out where its position is, you will find it somewhere, but then the interference effect will disappear. So it means that the measuring device, which will answer to the question, where is the particle, what is its velocity, this measuring device will perturb the state of the system in such a way that the wave aspect will disappear. And this is explained by the superposition principle and also gives rise to this very strange feature of entanglement, which means that if once two particles have separated, what you do on one has an immediate effect on the other. And this had been demonstrated in particular by the experiment of Alain Aspect 40 years ago, and this explains the Nobel Prize which was given in physics last year for this. But of course, the notion of entanglement was known since the beginning of quantum physics. It was one of the deep points of this theory, which explains why some theorists don't understand why you give so much emphasis to Aspect's work. They say it's obvious, it comes from the equation of quantum physics, and so you have to think about the connection between theory and experiments once again in this context. The last, and also all this is also contained in something that everybody knows about, even if has heard about, which is the Heisenberg uncertainty principle and the notion of Bohr's complementarity. So I don't have time to enter into more details, but I would just like to focus during the last minutes on the laser. I have started saying that the laser is a really fantastic tool, and I will just give you a few examples. In a laser, all the atoms which emit light emit it in step. All the photons which are emitted by light source have the same direction of propagation, the same frequency, and the same phase. Whereas in a classical lamp, like the lamps we have in this room, the atoms emit independently kind of chaotic light. So I like to think of laser as a tamed light, a domesticated light, as opposed to the weird light of the sun of classical lamp. So you can, with laser light, you can focus light on a small spot and accumulate a huge amount of energy on it. So you can achieve the fusion and the evaporation of matter, reach the temperatures as high as at the center of stars, millions of degrees, by concentrating energy of the laser. And on the other hand, if you use the laser in a very unexpected way, in a very non-intuitive way, you can use laser light to cool atoms. If you just send the laser light opposite to the direction of the atom, you can take a lot of momentum from the atom until they are almost at rest. And this is a mechanism of atomic cooling and atomic trapping, which led in particular to the Nobel Prize of Claude Cohen-Tanucci. And when the matter is very, very cold, the de Broglie wavelength becomes large, and you get new phases of matter that were imagined by Einstein following his work with Bose, so Bose-Einstein condensation. And it took 75 years from the idea of Einstein to the discovery of the Bose-Einstein condensate. It took also 50 years from Einstein discovering the principle of stimulated emission and the construction of the first laser. So this gives you a kind of time scale between the basic science and the possible applications. Another kind of application of laser light is the fact that it's ultra stable. It oscillates without skipping a beat on millions of kilometers. And this phase stability has led to the development of new atomic clocks. You can also superimpose laser beams which have slightly different frequencies in such a way that they interfere destructively after a very short time. And so you build a kind of bullets of light which have a duration of a few attoseconds. An attosecond is 10 minus 18 seconds. So you can have very small pulses of light, very propagating over space, which span a very short distance and pass over a given point in a few attoseconds. Just to give you an idea about what an attosecond is, if you take 1 second and use a logarithmic scale, an attosecond is as far from 1 second as the age of the universe is from 1 second. There's about 10 to the 18 seconds in the universe, and then the attosecond is 10 minutes 18 seconds. And you can explore this kind of time scale, ultra short time scale with laser light. So it has led, just to say that it's a very flexible tool for fundamental research. And also, of course, we know it's used in chemistry and biology and communication. And I will give you only a few examples. The first example I want to give you is the optical atomic clock. I come back to what I said at the beginning. What this clock is doing is that it is counting the frequency of an optical laser, which is locked to a transition in a very ultra-cold atomic sample. So you send the laser through the sample, you make sure that you are at the center of this very narrow atomic line, and then you count the frequency of your laser. It's oscillates at a frequency of 400 terahertz. A terahertz is 10 to the 12 hertz. So we are now in the range of 10 to the 14 hertz, which is 5 orders of magnitude higher than the optical microwave clocks. And indeed, you gain this precision. The precision is now 5 orders of magnitude more precise than the GPS clocks. And it means that if you had started 2 clocks of this kind at the beginning of the universe, they would not differ from each other by more than 1/20th of a second. Now, these clocks had been used a few months ago by a group in Boulder, Johnny E., the group of Gila in Boulder, to look at the difference of the clock ticking rate when you move the clock up and down by 1 millimeter in the gravitational field of the Earth. This is called the gravitational redshift. And they were able to observe this shift, which means that now the clock is a device which measures tiny variation of the gravitational field at the millimeter scale in the gravitational field of the Earth. And I think this illustrates very clearly the kind of Salvador Dali soft clocks painting. I think Dali was made this kind of painting when the general theory of relativity became fashionable in the 1920s. But now you see that the clocks are really like that way. When the clock, if the clock is more than a few millimeters in size, the time does not elapse at the same rate at the top and at the bottom of the clock. And you have to take this into account. Another application that I don't want to discuss too long because I come at the end of this talk is that lasers have been instrumental to detect gravitational waves. You see at the bottom a huge Michelson interferometer. These are evacuated tubes in which light propagates in 2 orthogonal directions. And you look at the time it takes for the light to go from the beam splitter to the mirrors and back. And when the gravitational wave is coming, the change in the space-time matrix makes the distance a little bit bigger in one arm and a little bit shorter in the other arm. And so you see an interference effect. And you see at the top the kind of signal, the first signal which was detected, which is an oscillation produced by the collapse of 2 black holes, which were 1.3 billion light years away. So it took 1.3 billion years for this ripple of gravitational wave to reach the Earth, and the effect on the Earth was exceedingly small. I give you some orders of magnitude. In fact, the difference of distances in the two arms is only 1,000th of the diameter of an atomic nucleus. It's 1 part in 10 to the 21 or 22 compared to the distance between the mirrors. So it gives you an idea of the kind of precision that lasers allows us to achieve for measuring this kind of effect. And since then, this happened 7 years ago, a new field of astrophysics has developed, which is detecting not light, not electromagnetic radiation, but gravitational waves. And these kind of events are commonplace. You have thousands of black holes which are collapsing all the time and detect. And I think it's mind-boggling to imagine the kind of energy which are released here. In this event, 5 solar masses have disappeared in 1 second. Now, if you compare that to the sun is just 1 solar mass, and 1,000th of this mass will disappear in 5 or 6 billion years. Here, an event which is 1,000 times more important, involving more energy, happens in 1 second instead of 5 billion years. And the effect is so tiny at the surface of the Earth, and still we are able to detect it. And again, this is connected to Einstein. The gravitational waves come from the general theory of relativity, and the lasers come from the idea of stimulated emission. And in fact, Einstein had these two ideas within a few months interval, 1915, 1916. And of course, he had no idea that this would be converged for this kind of experiment 1 century later. Lasers can also be used to control atoms one by one. You see here 5 beryllium ions in the lab of David Winan, which was quoted at the beginning of the talk. Each ion behaves as a small star because it's irradiated by laser light and radiates light into a microscope. And you see here 14 calcium and then 30 calcium ions in another lab, the lab of Rainer Blatt in Innsbruck. Each of these ions carries an information which can be considered as a qubit. It can be in either of one of 2 states, and any kind of superposition of these 2 states can be manipulated and studied. And so this is, of course, a kind of abacus for quantum information. And this kind of ion traps are used to try to demonstrate the ability of this kind of system to manipulate and to process information in using the quantum logic, the fact that you have state superposition and entanglement. So I don't want to say too much things about that. On this slide, I just summarize very briefly my contribution, which is cavity quantum electrodynamics. What we do is to enclose an atom and a photon in a box which has very highly reflecting walls. So the atom is the smallest entity of matter, and the photon is the smallest entity of light. And so looking at how they interact allows us to study this interaction and to demonstrate quantum effects in the interaction. So what we can observe on this simple system, state superposition, situation in which the atom is at the same time in one state and the other, and the photon is at the same time here and not there. You can also test non-locality and entanglement. When the atom leaves the cavity, the state of the atom remains correlated in a quantum way to the state of the field left behind. And so we can do a lot of studies of this kind. What I want to stress is that Einstein and Bohr had the idea of a photon box back when they discussed thought experiments in the early 1930s. So, but you see the kind of photon box they were thinking about is completely different from the one that we have built, but the idea was the same. They try to imagine experiments in which you would be able to find out whether there is one photon in a box or not, they said by weighing the box in the gravitational field of the Earth. In fact, we do it in a different way, but the ideas of testing the principle of quantum physics by this kind of experiment is the same. And of course, they could not do the experiment at that time, and we can do them now because we have lasers, computers, superconducting materials, and so on. So just on this slide, I show you the principle of our experiment. We have a cavity which is made of 2 highly reflecting superconducting mirrors, and we send through this cavity a special kind of atoms called Rydberg atoms. They cross the cavity one by one, They carry away information, and by exploiting this information, we can reconstruct the state of the field inside the box. For instance, we have been able to build field states in the box which are at the same time with one phase and the opposite phase. We call that a Schrödinger cat because it reminds the story of the cat which is at the same time dead and alive. And we could study this system and study how this quantum weirdness disappears very quickly. This is a phenomenon of decoherence. So let me conclude. People are often talking about the second quantum revolution. What do these experiments allow us to imagine in the future? And again, I say we have to be careful about that, but there are several possible directions. One is, of course, quantum metrology, which is to use the fragile features of quantum state to measure small effects with more sensitivity. And one example of that is, of course, the fantastic atomic clocks that I have described. If you use entanglement, if you entangle the atoms to which the laser light is locked, you could still increase the precision of these clocks by 1 or 2 orders of magnitude. And then a lot of new things might happen. You have quantum communication, which is to share qubits between two parties using either optical fibers or communication with satellites, and so this is quantum communication. You have quantum simulation. You can locate atoms, put atom on a well-defined lattice and emulate situations which occur in condensed matter physics and try to find out new states of matter, new phases of matter which can be useful and interesting. This is called quantum simulators, and a lot of nice physics is being made in this field, in particular in France. There are even startup companies which are starting to use Rydberg atoms to do this kind of physics. And of course, there is a holy grail of quantum computing, which is to build a computer which will use quantum logic to compute faster than classical computer. But there is a lot of challenges, a lot of research remains to be done to fight decoherence, and I don't want to say more about that. Just to conclude, I think what I have illustrated here is that everything starts by the observation of nature, the build-up of theoretical models, the prediction of new effects, which gives rise to novel technologies, for example, the laser. And then these technologies can be used to observe nature with even more precision. And this is a virtuous loop. It's a loop, the loop of research going from curiosity-driven research to application and back to curiosity-driven research. Since I was discussing the connection in basic and applied science, I want to attract your attention to this article or this small book which was written by Abraham Flexner. Abraham Flexner was the founder of the Princeton Institute for Advanced Studies back in the 1930s, and he was a big proponent of basic science. And of course, basic science is often considered by politicians as useless, something you spend money because just some weird people are curious, so you feed their curiosity with taxpayers' money. That's the way basic science is always considered, and one should concentrate the money on useful science. So Flexner had this provocative title, and of course he explains that what I have said in my talk, that apparently useless science is what is the basis of all useful science. And you never know what kind of basic science will be useful, but you know that without basic science you will have no application. And he was not the only one to think about that. I just quote also what Hendrik Casimir said. Casimir was one of the founders of quantum physics. He is the one who described the quantum vacuum for the first time, and he was also a big proponent of applied science. He had been the CEO of the Philips laboratories in the 1940s and 50s, and he wrote this: I have heard statements that the role of academic research in innovation is slight. It is the most blatant piece of nonsense that it has been my fortune to stumble upon. I think there is hardly any example of 20th century innovation which is not indebted to basic scientific thought. So I think our politicians have to understand that deeply. But I don't think you can restrict you can do basic science only because in the end it will be, or it might be useful. I think even if it's completely useless, it is essential. I'll give you an example. Why are we looking for exoplanets? We are looking for exoplanets because we want to try to find life outside our planetary system, outside our galaxy. We will never travel there, in spite of all the fantasies that people have about that. We will never colonize other galaxies because of Einstein, because of special and general relativity. But still, it is interesting to know, because it's part of a culture which replaced man in the universe. From Copernicus, we know that we are not in the center. We know that our galaxy is not at the center, and we now know, and we will know that life on Earth is not the only place where life is. So it's essential, and this is just culture and civilization. And Flexner wrote that, and I will end by last quotation, which is in the introduction of Flexner book, in which he tried to explain that beyond its usefulness, basic knowledge is an essential pursuit of mankind, and which is necessary to preserve the values of civilization, especially in dark and dangerous times. So I want you to meditate this. Is it not a curious fact that in a world steeped in irrational hatreds which threaten civilization itself, men and women, old and young, detach themselves wholly or partly from the angry current of daily life to devote themselves to the cultivation of beauty, to the extension of knowledge, to the cure of disease, to the amelioration of suffering, just as though fanatics were not simultaneously engaged in spreading pain, ugliness, and suffering. He wrote that in 1939, and I must say that 85 years later, it is still of a great actuality. So this is the end. If you want to learn more, a little bit of publicity, if you want to learn more and to have other examples of the importance of the history of the science of light, you can find it in this book, which is translated from French. For the time being, I think you can get it only on electronic version, but I hope it will be published and found in bookstores soon. So I thank you here for your attention.
We'll take a few questions.
Thank you, sir, for coming here. I am an undergraduate student here, so a very young person in this vast field of physics. So I am asking a question that how should young people approach the study of physics, the pursuit of this beautiful knowledge of physics?
It's a difficult question. Of course, you must have a passion for it, and you must try to recognize a problem or an area of this field which interests you and which you want to pursue. In my case, it was, when I started, I was first interested in astronomy. And then I went to quantum physics quite by chance because I had professors which were very good and charismatic at that, and I understood that I could apply mathematics as well to quantum physics as to astronomy. And it was a time when the laser started. So immediately I understood that the interaction of light with matter was a very profound, interesting field. Today there are many fields in which still question marks. I mentioned one in astrophysics, the search for exoplanets, and try to characterize the atmosphere of this exoplanet to find out whether there might be life there. So it's a lot of physics, a lot of astronomy, a lot of developing devices which measure with higher and higher precision the content of these atmospheres. If you are bolder and if you want to really tackle difficult questions, there is a big issue of making general theory of relativity consistent with quantum physics, which is not yet the case. These two theories are in some way conflicting, and if you want to really to understand what a black hole is, one has to work in this direction. But then the difficulty is to be able to confront theories with experiments. And the idea would be, for example, to build larger and larger accelerators But this is hard for a young physicist because the time it takes to build the accelerator might be decades, and you cannot just bet your own life, scientific life, on that. And moreover, I think that the accelerators have reached a size which makes it difficult to go much beyond that. But maybe what can be done, instead of trying to use brute force to increase the energy, a more subtle idea is to increase the precision of measurements, because with the kind of clocks I've been discussing in the end, you can maybe you can discover the existence of particles not by observing them directly, but by observing the effect they have on the spectrum of optical transition, the slight discrepancies which come from the fact that you have virtual particles being created all the time. And so there is this idea of increasing the precision of measurements in order to observe new physics. So I would say that going into the direction of increasing the precision of clocks, using clocks to measure gravitational effects, it's a field which might be fascinating, but it's for you to choose what you think. Yeah, there is also the fact that physics is essential. Instruments that you develop in physics are essential in biology, in neurosciences. For example, the kind of pictures you get of the brain using functional MRI and magnetic resonance imaging is astonishing, and I'm sure you will have great discoveries about the functioning of the brain using instruments which come from physics. So the fact to go into interdisciplinary science, connecting physics to biology is, I think, a very promising way to go. But I don't want to feel responsible for the direction in which we will go. As we know, it's impossible to predict what will be interesting in 30 or 40 years from now. You just have to bet and to be lucky.
In the back.
Hello, thank you very much for the presentation. My name is Margot, and I had a question in regards to exoplanets. Yeah. I was very thrilled to see that you mentioned the exoplanets, and as I follow a lot the research of Professor Sarah Seeger at MIT, and I was wondering what are the links that we can make in the research and the discoveries of the exoplanets with quantum physics?
I don't know. What I can say is that the research on exoplanet is based on the development of instruments which allow us, first of all, to measure the very small effects that the exoplanets have on the motion of the star around which they are rotating. And you need very sensitive optical ways to detect that. And the next stage would be to try to analyze the spectrum of the light coming from these planets. And so this requires a lot of development in technology for optical astronomy and ways to avoid all the disturbances that you have in the atmosphere of the Earth. So this is very technical and requires a lot of progress in technology. I think what you are alluding to is kind of conjectures about the fact that you have a deep connection between quantum physics and cosmology, which might lead to the possibility to travel faster than light. That's what you have in mind? Or?
Because from what I understood and from the research of Professor Sarah Seeger, she mentioned that the problems of the discoveries also for the exoplanets were all related to light. So I was wondering how quantum physics could be also used.
I think you have to work in the frame of a theory of relativity and quantum physics, and I think that we will be always limited by the speed of light to reach this outside bounds of the universe, and my belief is that it will never be possible, that we have that the laws of relativity are such that you will never be able to approach the velocity of light. It's a limit, but even get close to this limit requires a huge amount of energy. You would need to get close to bring a rocket at a velocity close to the velocity of light. You would need to expand all the energy on the planet. So it's completely unrealistic according to known theories. And I must stress the fact that the theory of relativity, both special and general, have been tested with a very, very high precision, and there is no hints today that there is something wrong about this fact. So I think it's very interesting to know, it's very interesting to study, but within the bounds of the actual theory.
Okay, thank you very much.
Yeah.
We'll take one last question. Maybe that's it. Yeah, the ones sitting on this. Yeah.
So like you said that right now it looks like we are on the shoulders of the giants that did those kind of research, those great research. My question is that with the advancement of technology these days, are we, and simulations, computer simulations are there, which exposes a lot of things which were not exposed earlier. We were not able to look into it experimentally. Those computer simulations does for us. So does the nature of doing research changing from more of an imagination and thinking to learning and doing? That's my question. So is the nature of research changing from hypothesizing, imagining more to just learning things, learning the so much abundant knowledge and doing?
Oh, I think you still need a lot of imagination. There have been some people are thinking what could be the use of artificial intelligence in science, and it's clear that artificial intelligence can handle a huge amount of data, and by analyzing this data, you might find maybe new phenomena. But in the end, you need the human mind to transform this data into creativity, into new ideas, into... My hope, maybe it's just a hope, my hope is that human intelligence will always be necessary to make real progress in science, and that artificial intelligence could be used as a tool to increase our power, but that you still need imagination. You mentioned also simulations. When you do quantum simulations, you try to emulate situations which might happen in real matter, and it can help you to synthesize new materials. But in the end, it's human imagination which has invented the ways to prepare and to manipulate these machines. So I think it's always a mixture of creativity, imagination, new ideas, and for that you need free thinking. You need the ability to think freely, not only in science, but also in humanities. And I think the ideal situation is a situation in which you will be free to think, to imagine, to go into new directions, and to go away from the fanaticism and the kind of ideas that Flexner mentioned in the sentence that I read in the end of my talk. The research, the scientific research, is part of a human activity which requires all these qualities: imagination, creativity, intuition, and luck also.
Thank you.
Yeah.
Okay, I'm sure there are more questions, but we'll take it offline, and we'll thank Professor Haroche again.
Thank you.
So on behalf of all colleagues from ISC and Quantum Research Park, here's a small token of appreciation.
Thank you very much. Thank you for your welcome.
So that brings us to the conclusion of this event. Thank you all for joining us. Thank you, Quantum Research Park and CEFIPRA for enabling this. We have high tea. Please join us, and maybe you can have some discussion. Not too many questions, but hopefully some. Okay. Thank you so much.